Okay. All right, so today I'm going to be going through section 1.6. And so the very first thing that we have here is, I guess it's really a definition. And these are our limit laws. So the definition says, suppose that C is a constant. And the limits, the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. Now, what that means again is, C is going to be a constant, okay? And then also A is going to be a constant that X is approaching. And these laws that I'm about to share with you, we can only use if these two limits exist, okay? So that's important. Then it says, the first law that we have is the sum law, and it says that the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Okay, so it turns out that when you take the limit of a sum, if both of those limits exist individually, then what you can do is you can figure out what each of those limits are individually, and then you can just add them together. This is called the sum law. Sometimes we'll say that the limit of a sum is the sum of the limits. Okay, so sometimes that's the way we say it. The second law that we have says that the limit as x approaches a of f of x minus g of x is equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. So again, it turns out that if you're taking the limit of a difference, then what you can really do is figure out what each of those limits are individually and take the difference of those limits. So the limit of a difference is the difference of the limits. Okay, what's important to keep in mind is that without these rules, we literally would not have a way to understand how to take the limit of a sum. This is the law that allows us to do that. Okay, so some people, a lot of times, sort of just glaze over these, and it's like, okay, well, just do the limit. Well, what do you mean by do it? Well, you just, you're going to take the limit of that part, limit of that part, and add it together. Well, that's, this is the law that allows you to do that. I mean, this is your set of instructions that makes that legal. The next one says the limit as x approaches a of some constant times f of x. Okay, so it turns out if you have some constant times f of x, then what you could do is you could pull that constant out and just focus on what the limit as x approaches a of f of x is. And once you find out what that limit is, then you can just multiply that limit by that multiplier c, and then you're done. This is called the constant multiple law. Okay. The next one says, what is the limit as x approaches a of f of x times g of x? Well, it turns out if you're taking the limit of a product, that what you could just do is you could take the limit of each of those functions individually, and you could multiply them together. So that's called the product law. Without these laws, again, we would not be able to figure out what the limit of a product is. Okay. So now, for the next one, it says the limit as x approaches a of f of x divided by g of x. And what turns out you can actually do is you can just take the limit as x approaches a of the top divided by the limit as x approaches a of the bottom. Now, you can only do this, again, if both of these limits exist, and, in this case, if the limit as x approaches a of g of x is not 0. Okay, that's an important thing to keep in mind. Now, I've defined all these things for the limit as x approaches a, but they'll also work for the limit as x approaches a from the left, or from the limit as x approaches a from the right. So something to note here is that these laws also apply to one-sided limits. Okay, so here's an example. It says use the limit laws and the graphs of f and g in the figure to evaluate the following limits if they exist. Okay, so let's look at this problem. Okay. This is 1, say this is -2. Those are going to be a few important values that we have. Also, this is 3. So this first function that I'm drawing represents f. All right, so this is the graph of f. Oh, and it's got one other point here. Let's see. Okay. And then the graph of g is going to look like this. All right, so this is the graph of G here. Okay. And so we have our graph, and so now here's our problems. Our first problem, it says find the limit as x approaches -2 of f of x plus 5 times g of x. All right, now we can only use the limit laws if both of these limits exist. So here's a question that we need to ask ourselves. Does the limit as x approaches -2 of f of x exist? That's the question. Does this limit as x approaches -2 exist? And the answer is, it looks like it does. If we zoom way in, okay, we're looking around x equals -2. And so we're only around this small region. So we're only going to be looking like from here to here. And so here's what's happening. As we're getting closer and closer and closer to -2 from the left, where it's like, what are the y values getting closer and closer to? So like we're looking. It looks like the y values are getting closer and closer and closer to 1. To y is equal to 1. Okay, how about from the right? If we approach from the right, we're getting closer and closer and closer to 1 again. So it looks like since they both agree, then that means that the limit's going to exist. And the limit's going to be 1. So that's good. Yes. And the limit as x approaches -2 of f of x is equal to 1. Okay. How about 1? Or how about g? I'm sorry. G. So we're still going to look at this small little group here. And so we're going to look at G, and we're going to ask ourselves, as we're getting closer and closer and closer to G, closer to -2 from the left, does it look like the y value is going to equal anything? It does. It looks like it's going to equal -1. And as we get closer and closer and closer from the right, it looks like the y value is getting close to -1. So it looks like the y value is getting closer and closer to -1. So the answer there is also yes. So that second question is, does the limit as x approaches -2 of g of x exist? And the answer is yes. And the limit as x approaches -2 of g of x, it looked like was equal to -1. All right. So that's great. So that means we can use our limit laws. So now what we have is this. We have the limit as x approaches -2 of f of x plus 5 times g of x. But since both of these limits exist individually, then that means the sum law says that we can take the limit of each part and then whatever those limits are, we'll just compute that. Now, this left-hand term, there's nothing else we're going to be able to do, but the right-hand term, law 3 says that constant multiple can get pulled out. So that means we're going to have 5 times the limit as x approaches -2 of g of x. Alright, so now, that being said, it looks like what we can do is we can replace all of this with 1 because we said that that limit was equal to 1. So that means that this is going to just be 1 plus 5 times, and the limit as x approaches -2 of g, it looks like we said was -1, so that means we can replace this with -1. So then we're going to get 1 minus 5, which is -4. Okay. So now let's go on and do part B. Part B, it asks us, what is the limit as x approaches 1 of f of x times g of x? Well, let's look at 1. Okay, if we notice, for f, it's going to be fine. The limit's going to exist, no problem. But if we're looking here at g, the limit's not going to exist. The limit as we approach from the left, it's -2. From the right, it's -1. And -2 does not equal -1, so that means the limit as x approaches 1 of g does not exist. However, I should say this. Because that limit does not exist, then that means we cannot use the limit laws. But if you recall, the limit laws will work for one-sided limits. So it's sort of a loophole. We can kind of get around our problem this way. So we can't directly answer this question because this question says, hey, what about the two-sided limit? The limit as x approaches 1. Well, we can't really directly use our limit laws because one of them doesn't have a limit that exists as x approaches 1. However, we can approach one from the left and one from the right and then see what happens. So let's do that. So there's two parts here. Part 1, that's going to be x is approaching 1 from the left. Okay? So let's look here. We now are going to ask the question, what is the limit as x approaches 1 from the left of f of x times g of x? Okay, so that's our sub-question. Because again, remember, if we can show that this exists, and if this happens to equal the limit as x approaches 1 from the right, then that would mean that this does exist and we're good. Remember, we're not saying that this does not exist. We're saying the limit as x approaches 1 of just g by itself does not exist. And remember that they both have to exist if you're going to use the limit laws. Okay, so we're going to break this into two parts. The limit as x approaches 1 from the left of the product f times g. Okay, well let's see. That's going to be the limit as x approaches 1 from the left of f of x times the limit as x approaches 1 from the left of g of x. And remember, we can do this, we can only do this because these limits are going to exist. You can sort of just look at them very quickly and be able to tell that they exist. So what is the limit as x approaches 1 from the left for f? Well, as you're getting closer and closer and closer to 1 from the left, it looks like the y value is getting close to 2. And then let's look at g. As you're getting closer and closer and closer to 1 from the left, then the y value for g looks like it's getting close to -2. And when you multiply these together, you're going to get -4. Okay, so that's the first part. So now we're going to approach from the other side. So part 2, what is the limit as x approaches 1 from the right? We're going to say, okay, we've got the limit as x approaches 1 from the right of f of x times g of x. Well, this is equal to the limit as x approaches 1 from the right of f of x times the limit as x approaches 1 from the right of g of x. Remember, here we're using the limit laws, and the only reason we're allowed to use the limit laws is because we know that this limit and this limit both exist. Why do we know they both exist? Because you can look carefully here, just pretty quickly actually, and you can figure out that the limit's going to exist. Now you can write these sub-questions if you like. I was just trying to, not make it so, because I know a lot of you have really been able to understand, that we're, one-sided limits from a graph, so. All right, so what is the limit as x approaches 1 from the right of f of x? Well, if we approach 1 from the right of f of x, we're going to get 2. And then if we approach g from the right, then that means we're on this part of the curve, we're getting closer and closer and closer to negative 1. 2 times negative 1 is negative 2. So now what we're going to ask ourselves is we know that the limit as x approaches 1 from the left of, this is all correct. We want to know what's the limit as x approaches 1 from the left of f of x times g of x, and we found that that was equal to negative 4. Okay. We also figured out what was the limit as x approaches 1 from the right of f of x times g of x. It was equal to negative 2. But these two things are not equal. So that must mean that this and this are not equal, unfortunately. They're not equal. Okay, so that means that we can say that the limit as x approaches 1 from the left of f of x times g of x is not equal to the limit as x approaches 1 from the left, from the right of f of x times g of x. Therefore, the limit as x approaches 1 of f of x times g of x does not exist. Okay, so now I think in class I was asked something like, well, do you always have to do this? Because generally, if one of the limits doesn't exist, is the product going to exist? Is it probably going to be unlikely? And I said, well, it's going to be unlikely. If one of the limits doesn't exist, it's probably going to be the case that the limit does not exist. The limit of the product does not exist, but not necessarily. There's examples you can come up with where this limit would exist, even though maybe say the limit as x approaches, say just g did not exist. I could show you an example just really quickly for a sum. So suppose you had a graph. I guess I'll call this like a side note. Well, okay, I'll just give it as another example. Consider the graphs of f and g. So here, suppose we have graphs of f and g. And suppose the graph of f looks like this. So this is the graph of f. And suppose the graph of g looks like this. So this is the graph of G. So now, maybe I'll fill it in to where the domain of both is all reals. So now, if we ask find the limit as x approaches 0 of, say, f of x plus g of x, we might look here and say, well, the limit as x approaches 0 of f of x does not exist. I'll just put does not exist. Also, the limit as x approaches 0 of g of x, the way we've drawn it here, does not exist. So that means we can't use our limit laws. But what we can do is we can break it up. So we can do the sided limits. So we can do part 1, the limit as x approaches 0 from the left. So we're going to do the limit as x approaches 0 from the left of f of x plus g of x. And that would be the limit as x approaches 0 from the left of f of x plus the limit as x approaches 0 from the left of g of x. Now from the left, you know, the only reason we're doing this is because they both exist from the left, right? So the limit as x approaches 0 from the left of f of x of f from the 0, so approaching 0 from the left, it's 1. And for g, if we approach g from the left, it is 2. So we get 1 plus 2, which is 3. Now for part 2, x is going to approach 0 from the right. So we're going to ask, what's the limit as x approaches 0 from the right of f of x plus g of x? Well, that's equal to the limit as x approaches 0 from the from the right of f of x plus the limit as x approaches 0 from the right of g of x. Remember, the only reason we did this is because we know that both of those limits exist. Because you can just look at the graph and tell. You know, you have to check that first. And so there's sort of an exception. I'll bring it up a little bit later. But the point is the only reason we're allowed to do this is because those limits exist. So let's go back and let's look at f. If we approach, if we're on f and we approach 0 from the right, we're going to get 2. And if we approach g from the right, we're going to get 1. But 2 plus 1 is 3. And these are both equal. So here we got that the limit as x approaches 0 from the left of f of x is equal to 3, but we also found that 3 is equal to the limit as x approaches 0 from the right. Oh, I'm sorry, I forgot to put something else in here. I said f, but it's f plus g, right? That was the whole big deal. Of f of x plus g of x. So the limit as x approaches 0 from the left of f of x plus g of x we found was equal to 3, but we also found that 3 was equal to the limit as x approaches 0 from the right of f of x plus g of x. And if they're equal, then that implies that the limit as x approaches 0 of f of x plus g of x exists. And it's equal to 3. Huh. Interesting. So that's an important point, okay? Now let me make a note here. We are only allowed to use the limit, and I'm capitalizing limit laws, right? So we're only allowed to use the limit laws if each limit exists individually. But instead of requiring that we check First, what we could do is we could assume they exist and use the limit laws, and if it turns out that one of the limits does not exist, then we consider all the work that followed our assumption as null and void. And we would go back and try something else. So here's what I mean about that. What I mean is, instead of having to go here and check, like imagine on this problem, problem A, instead of having to go and check and say, okay, does the limit as x approaches negative 2 of f of x exist? Yeah, okay, and it's 1. Does the limit as x approaches negative 2 of g of x exist? Yes, and it's negative 1. Okay. You could just go on ahead and take a leap of faith, so to speak, and just use this law. And when you use this law, make sure you understand that you are assuming that both of those limits do exist. And if it turns out at some point, like maybe here you found out, okay, well the limit as x approaches negative 2 of f of x, turns out it doesn't exist for whatever reason. If it was a different problem, it wasn't really 1, suppose that limit did not exist, then you have to go back and say, okay, well, turns out this limit does not exist, so this assumption that I made that exists is null and void. And you'd have to just scratch out your work at that point and say, hey, I got to go back, I got to do something else. Okay? So, and that's sometimes just, we'll kind of just make the assumption, we'll use the law, and then it's like, oh, well, you know what, we really weren't allowed to have used that law because we didn't have the criteria, the prerequisite criteria wasn't satisfied, so we've got to just throw it out. Okay? And then you could just have to try something else. So let me say here, back to example 1. Let's try to get one more problem out of it. And C is, what is the limit as x approaches 2 of f of x divided by g of x? Okay, well, if we go back up here and we look at this example, this first example, example 1, we'll call it, then it looks like if you're approaching 1, I'm sorry, we're approaching 2, right? Yeah. Yeah, and so, right. Okay, so if you're approaching 2, let's see here. G was in the bottom. It looks like the limit as x approaches 2 from the left is 0, from the right is 0. That means the limit exists, but it's going to be 0. Now, if the limit exists and the limit's 0, then that means that we have got a problem because this denominator is approaching 0. So that's an issue. The reason that that's an issue is because the limit law says that the denominator is not allowed to be 0. So since the limit as x approaches 2 of g of x is equal to 0, we cannot use law 5, that fifth limit law, the quotient law. So, okay, how are we going to evaluate this? Well, at this point, I'm going to kind of we're going to kind of answer this in an intuitive, like within an intuitive approach, and we're going to see later on. I'll give you guys a better way to solve problems like this. But if you look here at this graph, here's the idea. When you're approaching 2, so that's here, the denominator function, that g, it's approaching 0. The top function, f, it's approaching a number. It looks like, I don't know, maybe like 1.8 or something. 1.7, 1.8, probably something like that. So that being said, it looks like the top, it's getting closer and closer and closer to a number, but the denominator is getting closer and closer and closer to 0. Now, if you have a number in the top of a fraction, and the bottom, maybe it's not 0, but it's getting close to 0, let's see what happens. So let's just hold the top fixed. Okay, so let's see what happens. Well, so let's hold the top fixed. Let's say it's maybe 10. And the denominator, let's maybe pick the denominator to be 10. So that's like 1. Now let's leave the numerator 10. Let's shrink the denominator. We'll make it like 5. Now we get 2, okay? So that's not that big of a deal. So let's shrink the denominator again. Let's make it like 1. Now the whole value is 10. And let's shrink it less. How about we make it like 1/2? Well, the 1/2, you're going to invert and multiply, and that's going to flip, and that 2 is going to hit the 10 and make it 20. So now, if you get like really small down here, maybe you say like 1/100th, then that means that this 100 is going to flip around for invert and multiply, how you divide fractions. You can just Google that, and then that'll be 1,000. So now it's starting to get pretty big. If the denominator shrinks to something really small, maybe say like 1/10,000th, then this is going to become 100,000. So it looks like it's growing like without bound, and so that means the point is there's no limit, right? I mean, the limit's not approaching anything. Limit's not approaching anything. We talked about on 1.5 when that sort of thing happens. A lot of times we would say that the limit is equal to infinity. But that still doesn't mean that the limit exists. It's just more descriptive. So that's an important thing to note. Okay. So the bottom line is here in this problem, as a result, the limit as x approaches 2 of f of x divided by g of x does not exist. Okay. Now, to be fair, the numerator is not fixed as well. It's also changing, but it's getting really, really close to a specific number. So, in this illustration, I was having the denominator shrink to 0, and the numerator I was holding fixed, and that's not really fair because the numerator is also changing. But the numerator is getting really close to a number. So, I mean, this is like this is not an oversimplification. This is like a heuristic argument, but I don't think it's an oversimplification. I think it's close enough. So we basically say that as the denominator shrinks to 0, the numerator approaches a non-zero number, so this limit does not exist. So now what I'm going to do is I'm going to give you guys a new, just a few more laws here. But before I give you this next law, what I want to do is I want to kind of make a little investigation. Alright, so just for a moment, let's suppose that the limit as x approaches a of f of x is equal to b for some number b. So what we're going to do is we're going to assume that the limit as x approaches a of f of x exists, and that limit happens to be b, and that's a two-sided limit, and b is some number. It's got some limit. Okay. Well, if that's the case, then that implies that, or let's then consider, I should say, let's consider the limit as x approaches a of f of x all squared. Okay, well, if that's the case, the limit as x approaches a of f of x all squared would equal the limit as x approaches a of f of x times f of x. But if we use that third, or I think it was the fourth law, the limit of a product is the product of the limits, then that means that this is the same thing as the limit as x approaches a of f of x times the limit as x approaches a of f of x. So these two limits separately. Now, the reason we're able to do that is because remember that this limit exists. And since this limit exists, then that means it's the product of the two limits. But remember that this limit is b, this limit is b, so this is b times b, which is just b squared. So that's kind of interesting because we found that the limit, this just three-dot triangle means therefore. So therefore we found that the limit as x approaches a of f of x squared is equal to b squared. Now let's consider the limit as x approaches a of f of x all cubed. Now keep in mind we're still assuming that the limit as x approaches a of f of x exists and that that limit is b, the number b. Well, if we consider this, the limit as x approaches a of f of x all cubed would equal the limit as x approaches a of f of x times f of x times f of x. But if we use associativity, then now we're able to use the fourth limit law again, and we're able to say that the limit of a product is the product of the limits. So we get that the limit as x approaches a, so this is equivalent to the limit as x approaches a of f of x times the limit as x approaches a of f of x times the limit as x approaches a of f of x. But remember, each of those limits exists. That's why we were able to do this. We were able to do this step because we know that that limit exists, and that limit was equal to b. So this is just b times b times b, which is b cubed. So that's interesting. So that means that we found that the limit as x approaches a of f of x all cubed is equal to b cubed. So this leads us to the power law for limits. Okay, now we could actually prove this by induction, but you've just seen that it works for 2, it works for 3. There's no reason why it wouldn't work for more of them, because if you have more of them, then you just have more factors of f of x, but then you can use that limit law, and then it's going to just continue to work. It shouldn't matter how many of them you have, and that's what this definition is going to give us. We're going to call this the power law. And this is our this is our sixth law. This is our sixth law. So, this says that the limit as x approaches a of f of x all to power n is equal to the limit as x approaches a of f of x. Remember, so in our example, that ended up being like b, and then just raise that to a power of n. And this is true where n is any positive integer. Okay. So that's interesting. Now, if we there's two special limits that we need to use. I'll say limit laws. two special limit laws that we need to develop further limit laws. So these are sort of two kind of seminal laws that we need that we can use to then create many more laws. And these two laws are really easy to prove. Intuitively, you can kind of understand the idea. The first one says, this is a definition. It's called the constant law. Okay, and so it says that the limit as x approaches a of just a constant c. Remember earlier at the very beginning when we were first defining all these laws, we said that c was a constant. And so it turns out that the limit as x approaches a of a constant is just equal to that constant. Now there's a real easy proof for it, but essentially you could just imagine, intuitively this should make sense, because if you have a constant here, then it doesn't matter what x is, the output is always going to be that constant, because it's never changing, right? So if x is getting close to a, then that means it's still going to be that constant. I mean, it's literally never changing. So, I mean, you can think about it like as a horizontal line. I mean, you approach it from one side, you approach it from the other side, it's still this, it's still going to be this constant function. So, in other words, if we had a graph and over here was the origin, and this is like a, and you're approaching a from the left, you're approaching a from the right, and this is like y equals 2, for example, or you could call it just y equals this constant c, then that would mean that the y value is always going to be this constant. The y value is always going to be this constant. Doesn't matter which side you approach it from, So that's the idea. Sort of as a little intuitive proof, so to speak. All right, so now let's look at, there's another one that's really important. And it says this. It says that the limit as x approaches a of just x is always going to equal a. And again, it's a very straightforward proof. But we need this for some further theorems, or some further definitions, I should say. So now, here's what we're going to do. We're going to use, let me write this down. We're going to use Law 6 and Law 8 to produce Law 9. So here's the 9th law. Okay, it says that the limit as x approaches a of x to power n is going to equal a to power n, and that's going to always work where n is a positive integer. Now, the reason that this works is we said if this was any function, so remember in Law 6, we said any function, you raise it to a power of n, whatever that limit is going to be that limit raised to a power of n. Well, so the justification is this. What you could do is you could say that we have the limit as x approaches a of x to power n, but this is the same thing as the limit as x approaches a of x all to power n. And so this means that this function is like our f of x, y equals x in this case. So then what we can do is we can use Law 6 and we can bring the limit inside. So then we get the limit as x approaches a of x all raised to a power of n. But then by Law 8, this is equal to a to power n, and so we get a to power n, and there you go. So that's this is like our sort of proof. Let me call it a justification because it wasn't very formal, so sort of an informal proof. Here's our justification. This comes from law 6. We applied law 6 there, and then here we applied law 8, and we came up with this justification. So that's law 9. All right, well, so now let's look at another theorem, or I should say another definition. I would need some more to prove this to you, but in effect, you can think about a root. Remember that before I put this, consider that the nth root of x is the same thing as x to power 1 over n, and that's just an exponent property that you guys know from like algebra 1. Okay, so since that's the case, or I'll put because, yeah, well, I'll leave it like I had. Since this is the case, we are able to develop law 10. Okay, law 10. And I mean, I would need to do more to prove it to you, but I mean, if you'd like to see a proof, you can always see me after class. There's proofs of these in your appendix in the back of your text. But the idea is this. It says that the limit as x approaches a of the nth root of x is equal to the nth root of a. Okay, and really what you could do is you could say, in effect, we're using law 6 and law 8 again, because in this case the function f of x is equal to the nth root of x. And so that means that you have that the limit as x approaches a of f of x is going to equal, some value b. That being said, that means that the limit as x approaches a, well, I should say this. So since that's the case, essentially what we're doing is we're replacing this with the nth root of x, and then this becomes the nth root of a. And so remember that we know that the limit as x approaches a of just x would be a, and so that sort of kind of comes into play. But that's sort of a real kind of quick justification. In effect, I think that the approach that of using a general function and then the nth root, I think that whole idea about kind of applying law 6 and then law 8, that is probably more of what you would see for the next law, law 11. But basically, this is another definition that's also important, and this is true where n is a positive integer. And then our 11th law is this. It says that the limit as x approaches a of the nth root of f of x is actually equal to the nth root of the limit as x approaches a of f of x. And this is true in a general sense. So in other words, you can bring a limit inside of a root, which is very helpful. And that's where n is a positive integer. And I'll just say one thing about these last two. I'll say this also, and this is for 10 and 11. If n is even, then a is assumed to be positive. I'll put then we assume a is positive. And so that's because, remember, if a is not positive, then, or I'll say this, I mean, you could say greater than or equal to, really. But just the same, if we say that A is positive, then that's going to take away the possibility that this value is negative. Remember, if the value is negative and it's underneath an even root, then we have a complex number or something else. So we have to just make sure that we make this little statement. If n is even, then we assume A is greater than 0. Okay. All right, that's great. So now let's go through an example with all these limit laws. These are all these different limit laws that we have, and you're going to need to know all of these. So here's an example that we use for these. All right, so evaluate the following limits and justify each step. So that's an important component of an example like this. You have to say why you're doing which thing. So from which law, like which law makes you be allowed to do that. So here's the first example. We want to figure out what's the limit as x approaches 5 of 2x squared minus 3x plus 4. Okay, so that's what we want to do. Well, the first thing is we can use the difference law and the sum law, so we can make this the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. And this is using law 1 and 2. Remember, the first law was the sum rule, the second law the first law was the sum law, the second law was the difference law. Okay? So now, what's next? Well, the next thing we could do is we can pull constants out. So that was that constant multiple law. So that 2 can come out, and then we have 3 times the limit as x approaches 5 of x, and then plus the limit as x approaches 5 of 4. All right, and that's using law 3. So that's that constant multiple law, right, which says that constants, coefficients basically can come out of the limit. So now what we can do is we can evaluate this limit by saying, we can say, hey, what I'm going to do is I'm going to take the limit as x approaches 5 of x, and then I'm going to square that whole thing. And so here what I'm really doing is I'm really using like law 6. This is really like using law 6. Let me make sure that that's the right law. Pretty sure it's law 6. Yeah, that's really using law 6. In other words, I'm bringing the limit inside, and then I'm going to raise it to a power of 2. So that's what I'm doing. I'm using law 6. And then the next thing I have here is this is that special law we had, law 7. So if you remember law 7, oh no, I'm sorry, law 8. Law 8 says that the limit as x approaches 5 of just x should be 5. So this is now 3 times 5, and that came from law 8. And then we have the limit as x approaches 5 of a constant. So this is law 7. This is going to end up just equaling 4. And that's because of law 7. Remember, it's the constant law. Okay, so now what we have here is this limit right here should equal 5, and the reason it equals 5 is because of law 8. So this is going to become 5 squared, that's law 8. and then we have minus, and then you can just multiply here. That's 15, and then plus 4. So now we've got numbers. 5 squared is 25. 25 times 2 is 50, so we have 50. We're going to have to take away 15. When we take away 15, that's going to leave us 35. Then we're going to add 4 more, and we're going to get 39. So we get the whole thing is 39. Okay, let's do another one, B. So we have the limit as x approaches -2 of, we have x cubed plus 2x squared minus 1, all divided by 5 minus 3x. Okay, and we want to find the limit. Well, here's the deal. This is a quotient. So what we'd really have to do is we would have to make sure that this top limit exists. We'd have to make sure that the bottom limit exists. And we'd have to make sure that this bottom limit is not 0 before we're even allowed to use the limit laws. But as I mentioned earlier, instead of confirming that the limit as x approaches -2 of x cubed plus 2x squared minus 1 exists, and the limit as x approaches -2 of 5 minus 3x exists and is not 0, because that was an extra condition because it was in the denominator and you cannot divide by 0. So instead of confirming that, what we can say is this. We could simply assume they exist and use the laws as we're supposed to. If it turns out that one of, or I'll just say if it turns out that this assumption was wrong, then we just have to go back to this point. And understand all the work done is void. So in other words, the point is instead of having to go and confirm that the top's got a limit, the bottom's got a limit, that the limit of the bottom is not 0, we can just assume that all those things are okay and then just work it out. But if we find out later on that in the process of working out that actually, well, one of them doesn't have a limit, or if that the limit of the bottom is actually 0, then we have to come back to this point and just say, okay, all the work that we had done is void. You know, it's no good. Like, that assumption was wrong, so we really shouldn't have been able to have done that, but we didn't know. We were trying to save time, so just have to cross it out and try something else. Okay, so then it's like, all right, that's fine. So let's go ahead and try to make life a little easier. We have the limit as x approaches -2 of, and we have this x cubed plus 2x squared minus 1, all divided by 5 minus 3x. So that's going to equal the limit as x approaches -2 of x cubed plus 2x squared minus 1, all divided by the limit as x approaches -2 of 5 minus 3x. Okay, and so this used the quotient law. So this was law, I think 4, right? Or 5. This is law 5. Law 5. I'll just put law 5 here because that was the justification. And then, now remember, okay, so sometimes people will ask, like, Do you always have to do every step? Do you have to do, well, it depends on what your directions say. Okay, the directions for this example said evaluate the following limits and justify each step. That's what it says to do. So we're just complying with those rules. So, I mean, it just depends on the way your question's worded. If your question just says find the limit, if it exists, then no, you don't have to, show every single step. It's okay. So we have the limit as x approaches -2. So now we can use that sum difference rule, and we've got of x cubed plus the limit as x approaches -2 of 2x squared minus the limit as x approaches -2 of 1. And that's all divided by the limit as x approaches -2 of 5 minus the limit as x approaches -2 of 3x. So what we used here was we used laws 1 and 2. Okay, because it was the sum rule and also the difference rule. And now we can pull our constants out. So we've got the limit as x approaches -2 of, so first of all, I'm gonna use something on this first part. This has no constant, so this is the limit as x approaches -2 of x, and then all cubed, so that's using that, what was it, law 6, I think? Yeah, law 6, right? Yeah. So this is using law 6. I'll just put a, let me just try to think about this. I'm just going to put like an L6 here to sort of indicate that that's the law that I used. And then plus, then I'm going to pull the 2 out, and I have the limit as x approaches -2 of, and I'm going to tell you what, I'm going to just try to combine, because, so the limit as x approaches, so I'm going to bring the 2 out, and I have the limit as x approaches -2 of x all squared, so I used L4, which was our constant, no, L3, I'm sorry, which was our constant multiple rule. And also, I used law 6. And let me just confirm here. I think in one of these problems I said I used, yeah, I did. I said using law 3, constants out. Okay, just making sure. Okay, all right, so that's good. And so then I have minus, and then this is the limit of a constant. So that's just going to equal 1 because of that constant rule. And so that was law 7, I think. Let me look here. Law 7. So let me put minus 1, and that's law 7. And then this whole thing is going to be divided by, okay, this is also a constant, so that's just going to be 5, and that comes from law 7. And then minus 3 times, and so then we have the limit as x approaches -2 of x. So I used that constant rule, that was law 3, right? The constants could come out was law 3. So now the limit as x approaches -2 of just x, that's going to be -2, and then it's being cubed. So all I did here was I evaluated the limit. I didn't, oh, well, yeah, okay, I guess I used a law there. The limit as x approaches a of x is just a. That was law 8. Yeah, that's law 8. So I use law 8, and then I have, here I have plus, and I have 2 times, so same thing here, -2 all squared, and that's also law 8, and then minus 1, and then that's all divided by, and I have 5 minus 3 times, and then this is the same thing, it's going to become -2, and that's by law 8. Okay, so now all I have to do is compute this. -2 cubed is -8, plus -2 squared is +4, and then times 2 is +8, and then minus 1, and then that's all divided by 5 minus, and then 3 times -2 is -6. Okay, and so then these two things add together to get 0, And so then I'm just left in the top with -1. And on the bottom I've got, this is going to become plus positive, and you get 11. So the whole thing is -1/11. Okay. All right, good. So now some people, like, at this point, they're like, man, like, why do we have to do all that work? Well, because it's important that you get used to these laws. You know, it's important. Trust me, okay? What happens is people, after a while, they kind of forget what's legal, what's not legal, what's allowed, what's not allowed, and then they just start doing things, okay? And so the things that they're doing, they're like, oh yeah, I'm just calculating the limit, but some of the rules that they're using, they're just making up, and they're not really rules, okay? So just doing a few exercises like this early on helps you kind of understand, okay, what laws are legal, what are the laws, how do they work, etc., okay? I mean, the truth is if you force people to go through algebra and every time they're solving an equation, they have to justify every law that they use, a lot of times it helps them understand, oh, like I was really using a law that like isn't even really a law. It was something I just made up. It's not really true. That's not how algebra works, and that's a very valuable insight. Okay. Are you going to have to do this always? No. Oh, no, of course not. But you're just learning, okay? So here's what some people are probably familiar with already. There's always at least a few people, if not several people, that already were aware of this before they even walked in the door. They probably realize, well, hey, you know, like it seems like we could have just plugged in, like, right? So in other words, if we had just taken, like in say problem A, if problem A, if we had just plugged in the 5 to begin with, then wouldn't that have just worked? And if we had taken on B, taken -2 and plugged it in, wouldn't that have worked? Well, yeah, turns out it would have, but there's very specific reasons why it works. So note in part A, or let me in part A of the exercise, f of x, the function that we were taking the limit of, was equal to 2x squared minus 3x plus 4. It turned out that the limit as x approaches 5 of f of x was equal to 39, and interestingly, f of 5 also was equal to 39. So in other words, if we had simply substituted 5 for x, we would get the right answer. If we had substituted -2 in part B, it also would have worked. So it turns out this substitution idea always works for polynomials and rational functions as long as the a value, in other words, the value that x is approaching, is in the domain of f of x. So for a polynomial, you don't have to worry about it because every polynomial has a domain of all real numbers. However, for the rational functions, you do have to make sure that it's in the domain. In other words, for the rational function that was given in part B, if it just so happened that -2 had not been in the domain, then that would have meant that it would have caused division by 0, in which case the denominator would not have been 0. Or I'm sorry, in that case would have been 0. And so that would have meant that -2 would not have been in the domain, and you could not have used this just plug it in business, because otherwise you'd get like, I don't know, 7 divided by 0, and then it's like, well, what is that? It's not 0, it's nothing, it doesn't have an answer, so you'd have to do something else. And we'll talk about those special cases, what do you have to do in a moment. So this produces a very, very nice property that everybody likes because they use it all the time. It's called the direct substitution property, and so this is another definition. Okay, this is not one of our laws though, but it's a property. It's called the direct substitution property. Okay, and here's what it says. It says if f is a polynomial or a rational function and a is in the domain of f, of which, remember, that'll always be the case for a polynomial. And remember, we're talking about a being a real number. I wanted to put a in quotes so that you understand that here I'm using the word a as like the number a, and here I'm using the word a as like a in English language. So anyway, a is always going to be in the domain if it's a polynomial, but if it's a rational function, not always, right? Because the rational functions have a few values typically that are not in the domain. So back to what I was saying, and a is in the domain of f, then it turns out that the limit as x approaches a of f of x is equal to f of a. Okay, so if somebody asks you in the future and they say, well, hey, like, how come, like, why is it you're allowed So if someone asks you, well, why is it you're allowed to make that substitution? Why is it you're allowed to substitute the value, and how come you can just plug it in? Why can you just plug it in? The answer is, well, hey, I have the direct substitution property, which tells me that it'll work for any polynomial or any rational function. Now, we didn't say that it works for any type of function that you've ever seen on planet Earth, right? I mean, there's plenty of other functions that are not polynomials, that are not rationals, okay? So we'll come up with a more general property later, but for now, this is the property that we have. Basically, let me give you guys a note here to kind of plant a seed. Functions with the direct substitution property are called continuous at A. We will learn more about this in section 1.8. Okay, only when a function is continuous are you allowed to make that Just like plug it in, no problem business. Okay, and we're going to see that later. So here's an example. What are you supposed to do if it's not continuous? Well, we're going to find out. Let me show you. All right. Find the limit as x approaches 1 of x squared minus 1 divided by x minus 1. All right, so I'm going to give you guys a little side note here. I'm going to make an important mention before we come back to this. So let me kind of mention this as a side note. Okay. So in the past, you may have seen exercises in an algebra class where you're asked to simplify. Okay, and then maybe you're given a rational expression, maybe something like x squared plus 2x plus 1 all divided by like x plus 1 or something like that. And maybe, yeah, maybe just something like this. And you're asked to simplify. Well, when you simplify this, you know what you're taught to do is you're taught to factor all the polynomials. And so the one on the bottom is linear, you don't have to do anything. But in the top, you've got x plus 1 times x plus 1. Or you could call it x plus 1 all squared. And then, generally, this detail gets glazed over, and it's a really important detail for calculus. People say, oh yeah, and then you can cancel. And you're left with x plus 1. Well, that's for the most part legal, but there's a very, very important detail that's sort of glossed over that really makes this not true. This is actually not true. So, if you've been taught this is actually not true. There's one very important detail that makes this not true. Here's the important detail. When you look at it here, x cannot be negative 1. Because if x is negative 1, then let's look down here. If x was negative 1, then the bottom would become negative 1 plus 1, which is 0, and you cannot divide by 0. It's impossible to do that. You cannot divide by 0. Ever. Ever, ever, ever. Never can you divide by 0. But here, x can be negative 1. There's no problem with that. If you plug negative 1 into this function, this function right here, or this expression, you should say, maybe in this context we're dealing with expressions, you have negative 1 plus 1, which is 0, and that's no problem. So negative 1 is not in the domain of this expression, but negative 1 is in the domain of this one. So that means that these are not equivalent. They are not the same thing, okay? They are not the same thing. So here's what that means. That means to be legal, so in pre-cal you talk about when are two functions equivalent. And so in that situation you're talking about functions, you're in that context, and you say, well, two functions can be called equivalent if they have the same rule and the same domain. These are going to have the same rule, but they don't have the same domain. So the minute that you make that cancellation, you have to make a statement over here that x cannot be negative 1. If you make this statement over here that says, okay, x cannot be negative 1, and maybe you say, you know, like if x is not negative 1, you know, maybe to be more clear, we're saying if x is not equal to negative 1, then this is fine. We make this cancellation, and then we're good. And see, now they do have the same domain, don't they? We're telling you that this is the same thing as, you know, this, this, and this. They're all equivalent, and they're all exactly the same thing. And we're telling you that for this one, we're not going to allow you to put negative 1 into it. Because if we allow you to do that, then it's not equal anymore. But now we're saying it is equal. We're just going to restrict the domain, and we're going to say, hey, we're going to allow the domain to be anything except we're still not going to allow it to be negative 1. Then we're good. Okay? So that's an important thing to mention, because what's interesting is if you go back in your books, and you go back, you look in your notes, you go back, you look in your textbooks or whatever, and you see when you were taught to do this stuff, generally there's like one little sentence, and it'll say, we assume no denominator is 0. And it'll say that like for all exercises or something like that. So then that means what they're trying to get you to focus on is they're trying to get you to focus on the fact that you can make this cancellation. Okay. Now, but that being said, let's look back over here. We're asking you now, find the limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, no problem. Well, let's figure out the limit here. So, in your text, they have an important thing telling you, you cannot use the direct substitution property. Why? Because we told you that you can only use the direct substitution property when this value is in the domain of this function. Well, if we look here, 1 is not in the domain of this function, so that's why we cannot use the direct substitution property. So what they do is they do this. They tell you, okay, well, it turns out that our function f of x is equal to x squared minus 1 over x minus 1. And if you factor the numerator, that's a difference of squares, and this factors as x plus 1 times x minus 1 all divided by x minus 1. And now you can make the cancellation and you can say that this is actually equivalent to x plus 1 as long as x is not 1. Right? All right, so that's fine. So now we've got an alternative form for f of x. So now we could say this. We could say, well, wait a minute. We're taking a limit. We're trying to find the limit as x approaches 1 of x squared minus 1 over x plus 1. That's what we're looking for. But we can say we're inside of a limit. Because we're inside of a limit, remember, a limit doesn't care what happens at 1. It cares what happens around 1. Okay? A limit literally does not care what happens at 1. The function could be defined, the function could be undefined, it doesn't matter. The only thing that a limit concerns itself with is what's happening when you're close to 1 on either side, but not 1 itself. So as a result, we say, oh, okay, well, let's see. Then that means that this limit is equivalent to this limit. We can say that. So you can actually show the work. You can say the limit as x approaches 1 of x squared minus 1 all over x plus 1. That's going to be the same thing as x plus 1 times x minus 1 all over x plus 1. At least the limit as x approaches 1 of x squared minus 1 over x plus 1 is equal to the limit as x approaches 1 of x plus 1 times x minus 1 all divided by x plus 1. And then we can say that, well, we're inside of this limit. I'm sorry, I wrote this problem incorrectly. It was supposed to be a minus in the problem, and I said plus. Okay, and so now, as a result, that means we can make this cancellation because we're inside of a limit. And it's still going to be an equivalent statement because the limit does not care what happens at 1. So it's almost like implied. See, we don't have to make the statement here that x cannot be 1 because it's already implied. It's like, well, we're inside of a limit, so if this is true or this is true, we don't care. In either case, we're still going to take a limit, and the limit doesn't care. So you don't have to go off to the side and make that special statement and say, oh, well, x doesn't have to, or x can't be 1 because the limit doesn't concern itself with it, and so we can just do that. And now this is a new version of the function that we can use the direct substitution property in. So now we can use the direct substitution property. We can plug it in. We get 1 plus 1, which is equal to 2, and that's the right answer. So it's important that you guys understand, you know, like I could, you don't have to understand this special business about how x can't be 1. You don't have to understand this whole, you know, that the limit doesn't concern itself with what happens at 1. It only concerns itself with what happens around 1. You could totally not understand any of that information and be able to figure out this, but it's important for you to understand that information because otherwise you don't really know what you're doing. Okay, that's why it's so important. You know, I mean, like, I could just teach, you know, like I said, like I could teach somebody that doesn't really have any concept about what's happening. Oh, well, just take one and plug it in and then see what you get. And then if you get something where you have, you know, a division or division by 0, then that means it's not in the domain. You're going to have to figure out something else. Typically what that means is that limit does not exist. But it might be that we write infinity depending on the situation, or negative infinity. But just the same, you know, I could tell people, oh, well, if you end up getting 0 over 0, which is called an indeterminate form, and I'm going to go through that in a moment, that, you know, oh, yeah, you can just, you know, you're just going to do some algebra tricks and factor, and then you're going to get 2. But it's still really important that you guys understand why this is allowed. Okay? All right. So now, that being said, we have some more exercises to go through. Well, this actually brings up an important property, an important note, I should say. So I'm going to note here that if f of x is equal to g of x when x is not equal to a. So if for every other value, for example, the f of x is equal to g of x, for every value except maybe for a, then the limit as x approaches a of f of x will equal the limit as x approaches a of g of x. That they'll have the same limit, provided that the limit exists. And all that's saying is it's just saying, you know, if a limit even exists at all, then if f and g are two functions and they're equivalent everywhere, they're equivalent in every sense, they have the exact same domain except for maybe one value, except for maybe the possibility that x cannot be a. And if x cannot be a for maybe one of the functions, but it can be for the other one, it's not going to matter. They're going to have the same limits, you know, and that's all again if that limit even exists. Okay, so that's a really, really important fact. Okay. All right, so now let's look here at an example. And this is, I think, a good example to highlight this. You're given a function here. It says find the limit as x approaches 1 of g of x, where we're told here that g of x is a piecewise defined function, and it's equal to x plus 1 if x is not 1, and it's equal to pi otherwise. So in other words, it's equal to pi if x is equal to 1. So this is a piecewise defined function, okay? And so this function has a domain of all real numbers. It tells you, hey, this function for any value in its domain is going to be equal to the rule x plus 1, except for one value, 1. When x is equal to 1, it's not actually x plus 1 anymore. Instead, the y value is just going to equal pi. Okay? So what that's going to look like is this. This is a graph of it. Okay, so we've got x plus 1, that's a slope of 1, a y-intercept of 1, so it's going to look like this. Okay, and then it's got a hole at 1, but at 1 it's actually equal to pi. So this y value would have been 2, but it's actually going to end up being like about 3.14159.265, blah, 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 etc. Okay, so I'm just going to put this as like pi. Okay. All right, so that's what this function is going to look like. The question is, what's the limit? Okay, what's the limit as x approaches 1? Well, we're trying to figure out the limit as x approaches 1 of g of x. Well, hey, no problem. Like, no problem. You can look at the graph and you can tell what's going on from our conversations before. If you're approaching 1 from the left, you're going to get 2. From the right, you're going to get 2. So the limit should be 2. But now you can see that really this limit, see, we don't care what happens at 1. We care what happens around 1. And for every value of x that's around 1, the rule is actually the rule x plus 1. So that means that this limit is the same thing as the limit as x approaches 1 of x plus 1. And you can plug it in now, and you're going to get 1 plus 1, which is 2, and that's the answer. So what's important you guys understand is, are we saying that g of x is equal to x plus 1? Are we saying that the function g of x is equal to x plus 1? No, that's not what we're saying, because it's not true. The function g of x is not equal to x plus 1. It's equal to x plus 1 if x is not 1, and then it's equal to pi if x is 1. But we're taking the limit as x approaches 1. So since we're inside of a limit, that means that the limit doesn't care what happens at 1. It cares what happens around 1. And so that means, since we only care what happens around 1, this is the function everywhere else except for 1. So that means around 1, x plus 1 is equivalent to g of x. So it's like saying, again, g of x is not equal to x plus 1, but we're saying, well, when we're around 1 but not 1, then g of x is equal to x plus 1. So that's why you can't make this statement. Now, if we had made the statement that g of x is equal to x plus 1 if x is not 1, then that would have been legal. But if you don't make this extra statement, then that's not a true statement. And why don't we have to make that extra little statement inside this limit? Because it's already implied because it's in a limit. Okay. So now here's another example. Evaluate the limit as h approaches 0 of 3 plus h all squared minus 9 divided by h. Okay, well, now let's see. Is the direct substitution property going to hold? No, because if you take 0 and you try to plug it in for h, then you've divided by 0, and you can't do that. 0 is not in the domain of this function, so that means you cannot use the direct substitution property. It's not allowed. So we're going to have to figure out something else. So let's see here. We've got the limit as h approaches 0 of 3 plus h all squared minus 9 all divided by h. So let's do something algebraically to try to manipulate this thing. So this is the same thing as the limit as h approaches 0 of, and now let's, I don't need these brackets really, and so I don't really need them here either. Okay, and so now let me go ahead and put them in. Okay, so let's go ahead and expand this this binomial. So we have here 3 squared plus 3h. I'm sorry, 6h plus h squared, and then that's minus 9 all divided by h. So remember, also 3 squared is 9, right? And so now let's see here. This 9 and this negative 9 are going to add together to get 0. So now we're left with the limit as h approaches 0 of 6h plus h squared all divided by h. But now we could factor out an h, and we're left with 6 plus 8, and we're factoring h in the top. And we're left with h times 6 plus h all divided by h. And now, because we're in a limit, and because we know that h cannot be 0, we can make this cancellation. And again, we can only do that because we know h is not 0. So now we've got the limit as h approaches 0 of 6 plus h. And then this is equal to 6 plus 0, which is 6. See, now we were able to use the direct substitution property. We can use DSP now, the direct substitution property. Okay. All right. Let's look at another example. Okay, we're asked to find the limit as, now it's t. So we're asked to find the limit as t approaches 0 of the square root of t squared plus 9, all divided, I'm sorry, t squared plus 9 minus 3, and then that's all divided by t squared. Okay, we're going to have to figure out something, because can we use the direct substitution property? No, because if we did, then we would get 0 in the denominator, and that's not going to work. So we're going to have to do something else. So let's see here. We've got that the limit as t approaches 0 of the square root of t squared plus 9 minus 3, all divided by t squared, is equal to, well, what can we do? There turns out to be, there's a trick here. It's called rationalizing the numerator. If you're not comfortable with this trick, you're going to want to Google rationalizing the numerator or Google rationalizing a denominator, and then you can learn how this works. But basically what I'm going to do here is I'm going to multiply this fraction top and bottom by the conjugate of the numerator. So it's the same exact statement as the numerator, except instead of a minus, see, this was a minus, now for the conjugate it's a plus. And this is just multiplying by 1. So it used to be that we were doing this, we were finding this limit, but now we're multiplying by 1. So when we do that, you would have to FOIL here. Okay, you'd have to FOIL between here, but you don't have to FOIL between there if you can realize that this is just a difference of squares. This is an expanded form of a difference of squares. Something, so like a minus b times a plus b. So as a result, you can just use the fact that it's a difference of squares, and you're going to get that it's t squared plus 9 minus 3 squared, which is 9. And that's all divided by, and in the denominator I'm not going to distribute. I'm going to leave it as two separate factors. So now what we can do is, if we notice that this plus 9 and this minus 9 are going to add together to get nothing, and so we get that we have this t squared divided by t squared times the square root of t squared plus 9 plus 3. And now we can make this cancellation, and again, we can only make this cancellation if t is not 0. So we would have to make a statement, oh yeah, where t is not equal to 0, but we don't have to make that statement because we're inside a limit. And since we're inside a limit, whether t is equal to 0 or not, they're going to be, the expressions would be equivalent. So we're going to be left with 1 over the square root of t squared plus 9 plus 3. So now when we plug in 0, we're going to get 1 divided by 0 plus 9, the square root of 0 plus 9 plus 3. So now we can use the direct substitution property. So now use the direct substitution property. And when we directly substitute, see, once we directly substitute or once we evaluate the limit, then that's when we stop writing the limit statement. We're left with, this is 1 over, and we've got the square root of 9, which is 3, and plus 3, so that's 6. So 1/6. All right. So now there's an important theorem, which this is something I've already told you guys. I told you guys in the last section. It says that the limit as x approaches a, and we already used this. We used this earlier when I showed you guys that last graph. The limit as x approaches a of f of x is equal to L, and this is true if and only if, so I won't use this double arrow. I'll write out if and only if the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, and that both of them were equal to L. So in other words, the limit, the one-sided limit, the left-handed limit, for example, of f of x is equal to L. The right-handed limit is also equal to L. So that means that the two-sided limit exists, and the two-sided limit is L. Okay, so let's look at an example here. That might seem entirely obvious, but this is going to help us with a complicated problem. We're asked to show that the limit as x approaches 0 of the absolute value of x is equal to 0. Okay. Well, you could imagine that this is true by looking at a graph. This is the graph of y is equal to the absolute value of x. You can see as we approach 0 from the left, we're going to get 0. As we approach 0 from the right, we're going to get 0. So that means that the limit exists and the limit's 0. Okay, but why am I showing you this then? The reason I want to show you guys how to be able to figure out this algebraically. So recall the definition of the absolute value of x. The absolute value of x is defined to be a piecewise defined function. It's equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. So in other words, here's the idea. It would actually look like this, but then we have a solid line with the other one. So that's what makes it just be a solid point. So it's just the graph y equals x. So, slope of 1, y-intercept is 0, up 1 over 1, up 1 over 1, up 1 over 1. It's just the graph of y equals x when we're looking at it when x is 0 or when x is anything that's to the right of 0. And it's the graph negative 1 times x. In other words, you got a slope of negative 1, so down 1, right 1, down 1, right 1. Still goes through still has a y-intercept of 0, and that's going to be the case anytime x is to the left of 0. So it's these two different functions in two different places, okay? But it makes one single function, and it's got a domain of all reals. Well, look, we're looking at the limit as x approaches 0. So that means that there's not one rule that governs the limit as x approaches 0. There's two different rules, and it depends on which side you're on. So what we do know is this. We know that since the absolute value of x is equal to just x when x is greater than 0, then that implies that the limit as x approaches 0 from the right, so from the right of the absolute value of x would equal the limit as x approaches 0 from the right of just x. Okay, now that's the same kind of argument that we made in that first piecewise defined function with that pi business. And for this, you can use the direct substitution property, and you're going to get 0. Now, since the absolute value of x is equal to negative 1 times x for values of x that are less than 0, that implies that the limit as x approaches 0 from the left of the absolute value of x is equal to the limit as x approaches 0 from the left of just negative 1 times x. But that's the same thing as 0, but you could pull the negative out, or you could just, at this point, really, you could say you don't need to pull the negative out. You just say I'm going to use the direct substitution property. You're going to plug in the 0. You're going to get negative 1 times 0, which is 0. Okay, so since that's the case, let me put that in parentheses. Since that's the case, what we've done is we've shown this. Since the limit as x approaches 0 from the left of the absolute value of x is equal to the limit, well, I'll put is equal to 0, and that's the exact same thing as the limit as x approaches 0 from the right of the absolute value of x, that implies that the limit as x approaches 0, the two-sided limit, exists and is equal to 0. And that's by Theorem 1. Okay. Now, let me show you an example of a limit that does not exist. Okay. Prove that the limit as x approaches 0 of the absolute value of x divided by x does not exist. Okay, well, first let's look at a graph and let's agree that it's got to be the case using the concepts that we've discussed early on. Okay, so you could either make a table or not. You could just imagine, remember that the absolute value of x is equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than or equal to 0. Or, I'm sorry, less than 0, not less than or equal to. Just less than. Okay. Well, since that's the case, then that means that the absolute value of x divided by x is going to equal x divided by x. That's if x is greater than 0. And that's going to equal 1. Also, that the absolute value of x divided by x would equal negative 1 times x divided by x. And that's if x is less than 0. And that's equal to negative 1. Now, what about equals 0? Well, if x is equal to 0, this doesn't exist. You can't divide by 0. There's, and I'll put the absolute value of x divided by x is undefined. Now, notice I'm not talking about a limit, so I didn't say that the limit does not exist. I said that this expression or this function is undefined if x is equal to 0. So we kind of have this trichotomy. We broke it into 3 different cases, basically. So what this function is going to look like graphically, and you could just graph it on a calculator or something like that, but I'm doing this to show you what the graph looks like. It's just the solid line y is equal to 1 as long as you're to the right of 0, and it's the solid line y is equal to negative 1 when you're to the left of 0, and when you're at 0, it doesn't have any definition. It's undefined. It's completely undefined there. So it doesn't have a domain of all reals. That being said, now that we have a graph, you guys can believe what I'm saying. If we take the limit as x approaches 0 from the left, we're going to get negative 1. From the right, we're going to get positive 1. And so those two things don't equal each other, so that means that the limit does not exist, right? Okay, that's great with a graph, but how do you show that? Well, here's how to show that. We've kind of done a lot of the work over here. Here's how you can prove this. So we've got that the limit as x approaches 0 from the left of the absolute value of x over x. Now this is from the left, so this is going to be from the negative side. That's going to be the same thing as, so again, what I'm allowed to do is I'm allowed to replace the absolute value of x now with negative x. How come? Because the absolute value of x is equal to negative x when we're to the left of 0. That's what this says. So that's why we're allowed to make that replacement. But that's going to equal just negative 1. Okay. Now if we take the limit as x approaches 0 from the right of the absolute value of x over x, Now we're allowed to replace the absolute value of x with x. Why? Because it's equal to x when we're to the right of 0. But that's equal to 1. So now what we've done is we've shown that the limit as x approaches 0 from the left of the absolute value of x divided by x is equal to -1, and that's not equal to 1. And 1 was what the limit as x approached 0 from the right of the absolute value of x divided by x was equal to. So since that's the case, the limit as x approaches 0 of the absolute value of x divided by x, or the two-sided limit, does not exist. All right, here's another example. We have if f of x is equal to the square root of x minus 4 if, let me put a line here, if x is greater than 4 and f of x is equal to 8 minus 2x if x is less than 4, we want to determine whether the limit as x approaches 4 of f of x exists. Okay. So in this example, we could also graph this in a graphing calculator, but I don't know what it looks like offhand. So let's try to do it blind. Okay. We don't know what the graph looks like. So let's just try to work this problem out, and then we'll look at a graph. Okay. And so the truth is probably most of you don't know how to graph a piecewise defined function on a TI-83 or TI-84. You can do it. You have to use operators, and you have to say, like operators like where x is, greater than 4 and stuff. And you have to say and or and stuff like that. And to be honest with you, I've kind of forgotten how to do it. I'd have to look it up. But it's possible to do. Okay, so let's look at it here. So here's what we're going to do. We're going to first look at it from the left of 4. So what's the limit as x approaches 4 from the left of f of x? This is like part 1. This is like from the left. Four from the left. X is approaching 4 from the left. So we're going to say what's the limit as x approaches 4 from the left of f of x? Well, if we're to the left of 4, that means that the values are less than 4. And if the values are less than 4, then the function means this. So that means that really the limit as x approaches 4 from the left is actually equal to 8 minus 2x. Now this is something I can use the direct substitution rule for, and I'm just going to directly substitute in 4. So we get 8 minus 2 times 4, but that's equal to 8 minus 8, which is 0. Okay. Now we're going to look at part 2. We're going to look at what happens when x is approaching 4 from the right. Alright, so we have the limit as x approaches 4 from the right of f of x. Okay, and that's going to be the same thing. So if we're to the right of 4, then that means that the values that we have are greater than 4. So that's these. So that means that now f of x looks like that. It looks like the square root of x minus 4. So that means that this is going to be the same thing as the limit as x approaches 4 from the right of the square root of, what did I say it was, x minus 4. Okay. And so now this is something I can use the direct substitution property for, because I mean it's not a polynomial, it's not a rational function. Well, I'll say this. So the direct substitution property, we haven't exactly explicitly said that it works for this. So let me use another limit property. Let me bring it inside. So this is now this is a limit property that we've done. Okay, now what's inside that we can use a direct substitution property on, because that is a polynomial. What's inside there, and so this is the square root of, and you plug it in, you're going to get 4 minus 4, which is the square root of 0, which is 0. So now we've shown that the limit as x approaches 4 from the left of f of x was equal to 0. And that was the same thing as the limit as x approaches 4 from the right of f of x. It was also 0. Therefore, the limit as x approaches 4 of f of x exists. We were asked to determine whether or not it exists. We weren't asked to find what it is, although we did find it. So therefore, the limit as x approaches 4 of f of x exists and is equal to 0. Okay. So there's another example here. They use the greatest integer function for. Only reason I'm going to show you this is because if you've never seen the greatest integer function before, then you need to see it. Okay, the greatest integer function is defined by this symbol. It's this double struck bracket which is the largest integer that is less than or equal to x. Okay, for example, the greatest integer of 4 would be 4. The greatest integer of, like, say 4.8 would be, it says it's the largest integer that is less than or equal to x. So that would be 4 as well. So it's not typical rounding rules. It's like the floor function, basically. It's like saying whatever value you have, you're going to have to go to the left. Now, generally people are okay with that for positives once they understand, oh, like they say, oh, it's always rounding down. And that's kind of true, yeah. But you have to think about it. You have to look at negative values because it messes people up. First of all, what's the greatest integer of pi? Well, pi is about 3.141592665, blah, 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 etc. So 3.14, you know, that would, you know, we're going to go down to 3. It's like the integer part, basically, of a number. If you looked at the decimal expansion, you know, the decimal representation of a number, then it would be the integer part of it, basically. So we have here, suppose I have the greatest integer of the square root of 2, then the square root of 2 is about 1.414, blah, 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 etc. So that would be 1. These are the examples that you guys really need to see. What about, like, negatives? So what about the greatest integer of negative 1/2? Well, what integer is immediately to the left of negative 1/2? It would be negative 1, right? So this is actually equal to negative 1. People get a little confused with this, with negatives, because they're, you know, they're thinking, oh, it'd be like 0. No, it's not 0. It's going to be negative 1. You always have to go to the left. Okay. So here's what we're asked to do. We're asked to show, that the limit as x approaches 3 of the greatest integer function of x does not exist. Okay, the graph of it looks like stairs. You would have seen this before. I mean, we teach it in college algebra. We mention it in pre-cal. I mean, it's usually just only something that's mentioned. But it looks like this. Etc. It's going to continue. Etc. Okay. And so remember, this is the function, the greatest integer of x. This is what it looks like. All right, we have to show that this limit does not exist. You can tell it does not exist very easily by looking at the graph. This is 1, this is 2, this is x is equal to 3. You can see if we approach on the graph, if we approach from the left, we're going to get 2. From the right, we're going to get 3. 2 doesn't equal 3, therefore the limit doesn't exist. Let's show that algebraically, though. What is the limit as x approaches 3 from the left of the greatest integer function of x? Well, if we're approaching 3 from the left, this is 1, this is 2, this is 3, from the left, it's always 2. Okay? Because remember, these are values like 2.9, 2.99, 2.999. Remember, they don't round up to 3. They're going to go to the greatest integer part, which is the integer to the left of it, which is 2. So this is equal to 2. Okay, what is the limit as x approaches 3 from the right of the greatest integer function of x? Well, literally, this function is equal to 3, to the right of 3, 1, 2, 3. So, like 3.1, 3.01 is all of them are going to just go to 3. Now, you would replace it with whatever it's equal to, and then you try to use the direct substitution property. But I mean, you're just literally replacing with a constant. It's literally equal to 3. So that's it. So now you would just say since the limit as x approaches 3 from the left of the greatest integer function is equal to 2, which is not equal to 3, which is what the limit as x approaches 3 from the right of the greatest integer function of x was equal to, then the limit as x approaches 3 of the greatest integer function of x does not exist. Okay. Now we have an important theorem. We have two important theorems. Here's the idea. So the first theorem, we're going to, the book's calling it a theorem. I would call it a lemma. Because we're going to use it to help prove a theorem. But you could almost look at it as like you could also look at too as a corollary of this third theorem that I'm going to show you. But they're calling it a theorem. I'm going to call it a theorem. And this is the second theorem that we've given you. It says if f of x is less than or equal to g of x, when x is equal, when x is near a, when x is near a but not necessarily equal to a, and the limits of f and g both exist, as x approaches a, then the limit as x approaches a of f of x is less than or equal to the the limit as x approaches a of g of x. All right. So what's important that this tells us is, suppose one function is always less than or equal to another function. It's like it's dominating it. You know what I mean? Like this function's always bigger than this one. Worst case, they're equal. But g is always bigger, or maybe equal, but always bigger for sure. It's like it's dominating. It's like always on top, right? Then what you can say is, it's like, when I say dominating, I mean like it's always pushing it down. Like it's always like pushing it down. G is always going to be greater. Then it turns out that if both of these limits exist, if the limit as x approaches a, for example, of f of x exists, also the limit as x approaches a of g of x also exists, then it turns out that this limit will always also be less than or equal than g. Okay? So, in other words, if this function is always bigger than this function, it turns out that this limit will always be bigger than this limit. Okay? Oh, wow. Okay, so that's an important fact. Okay, then we have this third theorem, and this is a really important theorem. It's so important it's got a very famous name. It's called the squeeze theorem. Okay, this third theorem is the squeeze theorem. Okay, and here's what it says. It says if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly when x is equal to a. In other words, you know, as long as x is near a, we don't care what happens at a, but as long as we're near a, and if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, and they're both equal, say, to some limit L, then it turns out that the limit as x approaches a of g of x will also equal L. All right. So here's the point. Okay, here's the kind of what this theorem really says. It's kind of saying this. It's kind of saying, suppose you have some graph, okay, and suppose you're talking about x is equal to a. Suppose you have some blue function called f, as a matter of fact, let me do it this way. So this is f, and I'm going to change my a value. I'm going to put a over here, okay? And suppose you have some other function, h. And if you have some function that's always in the middle, then it turns out that the limits of so also here, if it turns out that okay, so let me start off with the explanation again. Okay, if we notice f is always the lower bound function, f is always on the bottom, f is just always the function of these three, for every x value it's less. The y values are always less than every other function. The function here, it's in green, this is the h function. It's always the function that's on the top, right? Its y values are always greater, always. And you have some function g, and it turns out that g is always like in the middle, okay? Now it could be that they're all equal, because it looks like when x is equal to a here, sort of it looks like they're all kind of equal, okay? But regardless, equal is okay, okay? If they're all equal, that's fine, or whatever. But the bottom line is h is like kind of like always on top, g is kind of always in the middle, and f is always kind of on bottom, okay? And if it turns out that the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, so that's this part right here, then it turns out that the middle function will get squeezed to also become that value. So it's like they're getting forced. It's like f and g are both like forcing, f and h are both like forcing g to become equal to that same thing. That's what the squeeze theorem basically says. They're saying that like it's like forcing it. Okay, so let's look at an example that highlights this. This is kind of the conical example to show this. Show that the limit as x approaches 0 of x squared times the sine of 1 over x is equal to 0. So show that this limit is equal to 0. All right, so first note we cannot use limit law 4. In other words, we cannot say, or it's not true, to say that the limit as x approaches 0 of x squared times the sine of 1 over x. We can't just say, oh yeah, this is equal to the limit as x approaches 0 of x squared times the limit as x approaches 0 of the sine of 1 over x. Why? Why can't we just do that? I mean, the limit law says we can do it any time that we have a product. Well, it says that the limit law says we can do it anytime we have a product and that each of these limits exists. But it turns out that this limit doesn't exist. You can look at a graph or you can look at a table. If you guys remember, I did an example in class very similar to it. This function, if this is 1 and this is negative 1, this function will kind of come in and then just like freak out. And do its thing. Okay? So regardless, that's kind of what happens to it. Okay? So ultimately, I mean, if you remember that we had literally no way to determine, because it started oscillating so crazily. I mean, there was no way to determine exactly where it was going to be located when you approach 0. So in other words, it literally reached a point to where in any infinitesimally small little region of the x-axis, for any really, really tiny value, that it would actually equal all values between -1 and 1. The y values would. So as a result, like we cannot use this because this limit doesn't exist. That's why we can't use it. So what are we going to do? Well, we can use the squeeze theorem. The sine of anything is always bounded between -1 and 1, right? So since that's the case, since the sine is always bounded between -1 and 1, that means, so let me write that, since the range of the sine function is always between -1 and 1, that implies that -1 is always less than or equal to the sine of x, which is always less than or equal to 1. But we said that that's the range for the sine function, always. So that means it would also be the range for the sine of 1 over x. Because the sign of anything is always bounded between -1 and 1. Always. The sign of anything is always bounded. So that means that the sign of 1 over x has to be between -1 and 1 also. Okay. But now, if I multiply, so I'm going to multiply by x squared. And that's going to give me negative x squared, which is less than or equal to x squared times the sine of 1 over x, and that's less than or equal to x squared. So this is going to be like my f function, which is always the low. So that was in this drawing, that was like my blue function here. Then we've got my upper function, and this is like our h of x. So this is like always on top. So like that's the most powerful function. And so meanwhile this is like our g of x. So we've literally shown that an f of x is less than or equal to g of x, which is less than or equal to h of x. And if you're not very good with less than or equal to's and it's very confusing to you and you don't really understand the statement, just think about it this way. G is always bounded between f and h. That's what it means. Anytime you have that double less than, it's like what's in between is less than or equal to. You know, it's always bounded between f and g. It can equal f, or I'm sorry, it's h in this case. It can equal f, it can equal h, but it's always bounded between or equal to either of them. Okay? All right, so since that's the case, now we're going to use the next part of the squeeze theorem, which says, see, if I can show that this limit and this limit are both equal when we're approaching 0, then I'm good. And I can use the squeeze theorem. So now what we're going to do is this. We're going to check, or let me put, we're going to find, or instead, how about I just do this? I'll say we're going to show that the limit as x approaches 0 of negative x squared exists. Well, no, I don't want to say that. I want to say find. I'm going to go back with find. Find the limit as x approaches 0 of negative x squared. Well, this is a polynomial, so that means you can use the direct substitution property, and you're going to get -1 times 0 squared, which is just 0. Now we're going to find the limit as x approaches 0 of x squared. Well, if it's a polynomial, you can use the direct substitution property. You can plug in 0. 0 squared is 0, so that means that's 0. So now we've shown, so since the limit as x approaches 0 of negative x squared is equal to 0, which is the exact same thing as the limit as x approaches 0 of x squared, and since negative x squared is always less than or equal to this, to x squared times the sine of 1 over x, which is less than or equal to x squared, then it must follow from the squeeze theorem that the limit as x approaches 0 of x squared times the sine of 1 over x is equal to 0 by the squeeze theorem. Okay. All right. Well, that's all I have. I know it's a lot, but I figure you guys can just fast forward as you need to. I went through a lot of detail. If you don't need the details, you can skip forward, whatever you want to do.